be presenting a research on geothermal exploration in the Lunar volcanic field located in western Saudi Arabia. This study integrates remote sensing, surface temperature analysis, and geophysical data to assess the geothermal potential of the region. Let's start with our abstract. Global energy consumption is rapidly shifting towards sustainable sources due to the environmental concerns of fossil fuels. Our study focuses on evaluating geothermal energy potential within the Lunar volcanic field. By analyzing gravity and magnetic anomalies along with satellite-derived and land surface temperature data, we were able to identify subsurface features indicative of geothermal systems. The results show significant geothermal activities and support the effectiveness of combining physical and remote sensing techniques in geothermal resource assessment. For our introduction, as tradition, fossil fuel resources are phased out. Geothermal energy presents a promising alternative that is both sustainable and available year-round. Saudi Arabia, through its Vision in 2030 initiative, aims to diversify its energy portfolio. Geothermal energy, especially in volcanic regions like Lunar volcanic field, fits into this plan. However, geothermal exploration is often expensive and logistically challenging. Our study addresses this by leveraging public available geophysical and satellite data to identify high potential areas for geothermal development. For our geological settings and area, the Lunar volcanic field is one of the youngest volcanic regions in Saudi Arabia and lies along the Red Sea Rift, a tectonically active area. It consists of basaltic lava flows, volcanic cones, and fault systems, all of which suggest significantly geothermal potential. Historical seismic activity, including a 2009 earthquake swarm, further support this. Due to limited geological mapping, our study relies heavily on satellite and geophysical data sets to evaluate the area's geothermal viability. As we can see in Figure 1, which is a topographic map of Arabian Plate, it shows the major tectonic features and volcanic fields across the Arabian Plate. The Lunar volcanic field is highlighted, indicating its location relative to tectonic structure such as the Red Sea Rift and other harats. It emphasizes the tectonic setting and significance of LVS locations within a geologically active region. Next is Table 1, which is a detailed comparison between several harats in Saudi Arabia. This table compares key characteristics of several volcanic fields, including size, stratigraphy, volcanic features, and rock types. The LVF stands out with recent activity, complex volcanic feature, and a mix of olivine basalt and evolved rocks, making it a compelling geothermal target. For our materials and method, gravity and magnetic data were available over LVF using both ground-based and airborne surveys from different sources. The gravity data were processed using standard techniques, including corrections for instrument drift, diurnal variation, and topographic effects. The data were also filtered to remove high-frequency noise and to enhance the signals of interest. On the other side, the magnetic data were processed using the standard procedure. As you can see in the Figure 2, which is the generalized trend of Bouguer anomaly data of the LVF, which is under the gravity data. This graph displays the variation in Bouguer gravity anomalies across multiple stations in the study area. The trend reflects changes in subsurface density. Lower values correspond to less dense material, possibly indicating areas of geothermal interest, while higher values suggest denser rocks. Next is the data on magnetic survey. In 1962, identified potential geothermal activity in the Arabian Shield's subsurface geology. The survey examined Curie depth, magnetic density, and SRTM30 topography, with the spectral analysis used to determine the Curie point depth in the Harat Lunar region. Still under the magnetic data is the study study of area map of the LVF along with LST and NDI data samples shown in red. The map outlines the lunar year volcanic field. R shows 50 sample points in red, like I said earlier, used to extract land surface temperature and normalize difference vegetation index values. These special points are used to evaluate surface thermal anomalies and vegetation cover across the area during 2000, 2007, and 2021. Now let's proceed to our results and discussion. Remote sensing data offers many beliefs and applications for investigating volcanic hazards, such as frequent image coveraging and multispectral properties that allows the geological mapping of rock and structures. Under the volcanic components and remote sensing interpretation, the figure 5 of Bowyer anomaly map illustrates three distinct volcanic rock units in the LVF, classified using remote sensing techniques. These include older, intermediate, and recent lava flows, as well as volcanic cones. The spectral distinctions between these units help in understanding the volcanic history and identifying younger, potentially active geothermal zones. As for the figure number 6 is the heat flow is a crucial parameter in geothermal analysis, providing information on the amount of heat generated within Earth's crust and its transport rock to rock and soil. Next is the magnetic data interpretation, which shows in figure 7. The map displays magnetic intensity across the LVF. Negative anomalies are centered in LVF, indicating thermally demagnetized or altered rocks typically of geothermal zones. Positive anomalies are in the southeast and northwest. The contrasting zones help delineate possible geothermal targets. Next is the figure 8, which is the Curie depth map. This figure shows the depth of the Curie isotherm, the depth at which magnetic minerals lose their magnetism due to heat. Shallow Curie depths are observed in the LVF, which supports the presence of high heat flow and geothermal activity beneath the region. Next is the SRTM topography map. This topography map, derived from shuttle radar topography mission data, reveals the terrain elevation of the LVF. High elevation correspond to volcanic cones and domes, while lower areas may be sediment-filled basin. The topography helps assess geothermal systems that are influenced by faulting and volcanic features. For the figure 10, which is the 3D layer model, this model integrates Curie depth point, magnetic intensity, and topographic to visualize subsurface geothermal structures. Areas with shallow CDP, magnetic anomalies, and elevated terrain are potential sites for geothermal reservoirs. The visualization help is spatial correlating the different datasets. As for the table number 2 of Curie depth map, the table categorizes LST values into 5 classes based on temperature ranges, very low to very high. These thresholds are used to classify geothermal potential areas in LVF and visualize them in figure like the LST map and pie charts. Figure 11 is the land surface temperature variation of the LVF for the years 2000, 2007, and 2021. This figure presents LST maps for 3 different years. A significant rise in surface temperature is noted in 2007, corresponding with reported dike intrusion and volcanic activity. High surface temperatures are linked to geothermal anomalies, making this a critical figure in identifying thermally active zones. Now let's see in the figure 12, which are the land surface temperature variation of the LBF for the years 2000, 2007, and 2021. These pie charts show the percentage of the study area falling into different LST classes for 2000, 2007, and 2021. the portion of high and very high categories increased significantly in 2007 and remained elevated in 2021, suggesting sustained thermal activity in the LVF. As for the Table 3, the details of statistical analysis of qualitative classification of the LST for the years 2000, 2007, and 2021. This table quantifies the proportion of the area in LST class for the three observation years. A sharp increase in the very high category in 2007 from 8% to 30%, and sustained levels in 2021 indicates ongoing geothermal activity. For the table which is the details of the statistical analysis on land surface temperature of the LVF considering 50 sample points. It shows minimum to maximum mean and standard deviation values for LSD and NDVI across 50 sample points. It also includes the correlation coefficient between LSD and NDVI, which is consistently negative, suggesting that higher temperatures are linked with barren land common in geothermal fields. In table number 5, which are the statistical analysis of the subsurface temperature data from the surrounding area outside the LVF at the well location. It provides measured subsurface temperatures from well data outside the LVF, with temperatures reaching up to 32.8 degrees Celsius at shallow depths. This supports the inference of high geothermal gradient in the region. And for our last figure, which is the figure 13, the NDVI variation of the LVF for the years 2000, 2007, and 2021. This figure indicates NDVI values for 3 years, confirming that the study area is consistently classified as bare soil. Low NDVI supports the use of LSD for geothermal analysis, as vegetation interference is minimal in temperature reading. For the conclusion, geothermal energy is reliable baseload technology that can enhance grid stability and provide energy resilience without expensive storage solution. A study in Saudi Arabia aimed to detect geothermal anomalies in the lunar volcanic field using various geophysical approaches. Gravity and magnetic data were integrated to identify potential areas for exploration and development. Thermal infrared remote sensing was used to reverse the LST and identify areas with high geothermal anomalies. The study found that 100% of the area lies in bare soil, indicating the potential benefits of geothermal energy as a reliable baseload technology in Saudi Arabia. That's all for my presentation today. Thank you for listening.